Hello, everyone. Do you hear me? Yes, good to see you. Congratulations, making to the end of. Is that today's the last day or? Okay, last lecture. Okay, last lecture that you have to sit through. So, so wow, heliophysics, summer school, data-driven heliophysics exploration and discovery. This is a really my favorite topic. I've been doing research with data many years. And then before begin, I want to tell you the story of summer school. About 20 years ago, that's kind of scary. some decades ago, I was sitting where you were as a graduate student. So I went to summer school in south of Italy. Ooh, it's nice, right? I thought it's nice. Wow, right? So I got there, south of Italy, south of Naples. So there's no like it. I'm from originally from Japan, so all public transportation, everything arrives on time and stuff. And then south of Italy, right? There's a bus. So I was a student, I didn't have a car or anything. Actually, all the guests, all the instructors, about 20 of them, I think, um, they didn't have car. Bus didn't, sometime arrived, sometime didn't. So we basically got trapped for 2 full weeks. Students and then instructors there. Gorgeous beach, but nothing else. Just like a deserted village. What kind of a small village? It's very nice by the beachfront hotel. And then the title of that day, the summer school was NATO. It's interesting, right? NATO does things like that. NATO Summer School for Data Assimilation. So back that time, I didn't know what data assimilation was about, what is about, right? So that time, people are not talking about AI or machine learning. So I got there. And day after day, from breakfast, lunch, dinner, talked about data assimilation. And then I learned inside out of covariance. We were talking covariance over lunch with wine, right? So that's how I got into data science, I believe. So for future consideration for venue, maybe because like I just showed up today, right? Imagine we get cooked up for 2 weeks. We're gonna have lots of interesting time, learn together, solve lots of problems together. So so yeah, of course I learned about data science without saying that term, covariance, all that good stuff. And then the most important thing, looking back, what I learned there is how to ask a good question, how to formulate the problem. So, okay, you have to ask question first, what you want to do. You are in heliophysics. You want to solve the problem. You want to solve space physics problem, right? So start with that. You wanna yeah. So ask question what you wanna learn from data, right? Because this is about data driven discovery, right? So always make sure that really helped me. Yeah, make sure you ask a good question, and second, make sure you know how to formulate estimation problem or learning problem, right? So that's those are the two things, and I'll come back to it hopefully. If you get anything, I want you get that out of from my talk at well, all the lessons you learn for a week. Okay, so yeah, a bit about myself. I teach at the CU Boulder Aerospace Engineering Sciences Department. I teach data science, I teach filter, and then my domain is a ionosphere and a thermosphere and then heliophysics. And it's a surprising that I got to where I am. And then that summer school really changed the trajectory. So I'm curious. like if this, hopefully this is an impactful experience for you, right? And then you are just starting out. So I'm envy you because time is a bit different from when I started out. So I want to talk about, of course, I was asked to talk about PCA, application of PCA, K-means, but it's, I want that the underneath, like what you are doing here, learning these tools, going through all the lessons. I guess you're doing I guess some practice in the afternoon. You're transforming, I guess this is NASA, so transforming NASA data into knowledge, right? And that's, remember, so that's a question. And then so you should have burning question, right? So okay, so let's get to that. And then before we get to that, so I want to talk about scientific reasoning, right? This is a scientific, right? AI, ML, just like any other tools, can be used for anything, right? For good or bad, you are using that as scientific tool, right? And then so let's say here, data-driven science methodology, you start with observation. We mine data, right? Especially unsupervised method, go through the data and then look for emerging pattern. And then you do it carefully. You do it knowing what you're doing. And then you hypothesize. You actually discover underlying rules from data. And then maybe you arrive at theory, and that is an induction, right? And then, of course, I think I like to see myself as a data detective. Whenever I see big data, especially, what's hidden there, right? And so that's deductive way of doing that scientific reasoning. Of course, the opposite end is deductive. You start with theory, law of physics. You're here, meaning that you have some basics or quite good basics, right? And then, so then you start from theory. Maybe you can come up with hypothesis or you come up with a model, right? And then you fly satellites, right? NASA, we ask NASA, give us data, keep giving us data, right? Then we test your hypothesis and confirm, right? So anyhow, those are two branch. But nowadays, okay, one thing that you don't, you don't need to pick the camp, you can blend it in, right? Physics informed neural network. There are other ways to integrate in an inversion method and so. Okay, so just that. Okay, so statistical learning technique or machine. The machine is doing learning, but underneath there are lots of math and equations. It's important to know that. And then there are two big categories of learning you are exposed to this week: supervised and unsupervised learning. I'm gonna focus on application of unsupervised learning techniques that you learn. Big difference is that you don't have level data, right? You just have bag of data, X, right? Yeah. So, so this is like from my experience of teaching and my own research. I think this is a baffling question, especially now. You got the Python package, you got big computer, you got big data. Expectation is actually high. But also, yeah, but exciting time, right? So which way to go, right? And then, but like more than anything, I really want you to, well, okay, so I asked you, I told you two things, right? Well, what you really want to learn from data. Make sure that your research is guided by that, right? And then what do you want to learn from data, right? And then even that can be learned from data. Just ask these questions, right? Rather than like your advisor might set you in the wrong path too, right? I have to see myself if I'm doing that. But one more thing, actually I didn't list, know your data. Please, you got that good data from website, right? But those are actually taken by engineers and scientists, and then you have to make sure you know the data first. And then before doing something fancy with data, just plot it, just see, right? Yeah, so make sure you know the data, right? So those are the things that just before getting to the start line, do that. Okay, here you go. So yeah, so you not just given a lots of data these days. It's nice data. Some of them are curated for you to discover. Uh, and then also you're given a bunch of nice tools, packages, right? And then you probably know, right? You played around with the Python, yeah, packages. But then like bunch of them. Oh wow, right? And then anyhow, so these are you can see it at the downloaded from that website, scikit-learn, right? So you could make a decision. You know, you really have to have well, you could try out, but then just go through logical steps, which method is actually appropriate, and then in contrast against what you want to learn from data, right? Okay, so I'm gonna talk about today a bit about everything, right? Just have to watch the time. So you learn about k-means clustering, and then you do practice, and also a theory behind it. So now you are expert, yeah. That's how, yeah. Feature engine. So and then I want to talk about yeah, kernel version of PCA or PCA itself. You could use PCA. I think it's considered as a really powerful dimensional reduction tools, but they also could be used as a feature engineering. And this is the important part about feature selection. And then if you really exploring what to do, then using, projecting data to principal components or kernel version of that principal component that could help you. So game is that because you're given lots of tools, you got to kind of have a broad knowledge, and then you kind of have to try a lot. Some of the things well, maybe you should know what you're doing, but also you could try out. So that's kind of advantage. Yeah, any time comes with a challenge and an opportunity. So yeah, these are the things that you learn now. So clustering is about finding the natural groups from the data, right? Like we want to categorize data, and then I'm gonna give you, I'm gonna go over example of solar wind, and then it's rather than like really saying like solar, plasma velocity, solar velocity above 450 or whatever is a high speed or not. Like people do apply this domain knowledge, but we want to learn that the natural groups, what data tells us, right? So that's what that is. So we want to really understand that natural grouping that that data is telling you. One more story that I forgot to tell you. So have a good collaborator, interesting collaborator from UC Davis stats department. And then he, we all data scientists. And then he tells me that, oh, you torture data. You torture data enough. And then data will reveal the secret. Things like that. Anyhow, so you really have to kind of go through in a way that you really have to try out. Anyhow, well, you really want to have the spirit of data detective. You can even if you are doing data science, you can put lots of subjective thoughts to it, and then you have to examine: am I learning everything from data, or can I learn something, thresholding or something, criteria from data, or do I have to assign it, right? Okay, so this is something that you already learned. So we want to assign clustering. It's to assign each observation to uniquely labeled category. So these are discrete problem, and then so assignment is one and only cluster. Okay, so I guess Farzad gave you a bit different interpretation of it, but that's what I have here. Okay, so k-means algorithm is a simple one, not the EM or anything like that, the Gaussian mixture or anything like that. K-means algorithm is iterative method that minimize within a cluster variation. So you're really looking for similarity within a group. So as you learn that you have to define a similarity, like a bag of data, you want to divide into two groups, and then you want this group, though the data belong to this category, the other category, they want this to be similar within itself, and that's right. And then similarity is also you can pick that different kinds of similarity measure, and then the most typical one is squared Euclidean distance, as you learn. And then okay, so I hope so let's see, like in a further example, you've seen sort of RGB pictures, right? So those, if you think about, those are three-dimensional feature data, right? So I'm gonna show you example. These are also up to you to choose. You could pick. Well, obvious thing is the color, right? But then, like if you're dealing with images and then segmentation problem, but you can add lots of features where you can combine features into some, or map to the lower dimensional space. Okay, so pay attention. I think I try to be consistent in the slides, but I use D for dimension of the feature, that, and then N for the number of replications, right? Okay, and then K for number of cluster, and try to exclusively use K for that, but maybe I haven't managed. Okay, so within cluster variation, so this is all the same thing, just saying and define a bit different way. So how to find the basically grouping rule or categorization rule or decision rule, well, boundary rule, is a because make sure that you're looking for that rule to minimize within a cluster variation, right? And that's you could solve it. For example, like this is a simple k-means clustering algorithm. You assign all the data and into, like, you have to pick k, right? So that's one thing. I'm gonna come to that. Well, in practice, picking k could be done more objectively. Well, learn k from data, you could do that. And then also, I think this was also discussed in the previous lecture. So random assignment, like you pick k, and then each data, a bag of data. So now you seeing here is what is D? What is the dimension of this data that's shown in this super simple? Yes, 2. Good, right? 2-dimensional data. And then number of points is probably around 100, right? And then K equals 3. And then you go through this iterative procedure and then finding that 3 groups. Okay, 3 clusters, right? And then, so there are lots of subjective aspect or heuristic aspect to that, right? You pick the K out of nowhere, but well, you're gonna have to try. And then here, and then, you have, this is end up being a local minimum, right? Not the global search. So where you stop the iterative procedure is up to you to decide, but also that decision can be guided by the data, right? Like ideally you want everything to be guided by data. Okay, so here you go. So this is another kinds of simple example, right? So now, so you have RGB image of aura on the left. So feature space is 3, right? And then okay, I kind of feel like I want to cluster into 19 group, and that's, so you could do that, right? So this is segmentation of image into 19 clusters. Okay, so this is example, but so now I want you to introduce you to actual examples, and then heliophysics application example. Okay, So this is coming from textbook. I think space weather machine learning, the textbook. So this is chapter 16 and an appendix. And then it's actually hard to find a clustering example. And then this chapter, Heydrich Maynard's chapter 16, I believe, is really well written. And that's I highly recommend it. In fact, that's what I did to come up with example for you. So they're interested in learning solar wind classification rules, right? From 10 years of ACE data using k-means. And then they learn something, right? And then well, let's see. So usually solar wind, well, there are many researchers attempted to categorize solar wind, high speed, slow flows, like a CME or, all the correlation areas, all that, it's very, we have tons of data. It would be great that if we could actually categorize those data, because you don't need to go through ACE data, 10 years of ACE data. If the rules that tells you, okay, there's 7 categories or 3 categories, and this is a decision rule, then you can just use that, and then you can just study high speed if that's what you're interested in. But now, okay, so, well, you could actually use heuristic domain knowledge-based decision rules. Okay, so this is just from that paper that, okay, obviously on the left, so you just use that solar wind speed, high speed, and then slow speed. Solar wind could be categorized and then you could map to the different feature, row feature, which is density, proton density. So it looks like that. And then or you could use a bit more different type of atomic oxygen ions or carbon charge state ratios. And then those are those are the kind of the features that frozen into the solar wind early on when they leave the sun. And then it's a really good tracer proxy. So for example, so those are domain knowledge, and then you could do that. And then you could use Zhu and Jobrowski's 2015. They're using 4 different types of row features and then categorize into 4 different types. Okay, you could do that. Okay, but can we learn these kinds of decision rules really from data? And then, so it's an open question, right? So then can we do that with k-means? Okay, so these are, this is what they use as raw features. And then in machine learning, features can be directly observed parameters like this one, solar wind, or taking a ratio of charge state, for example. So these are, I would call this as a raw features, or you could actually engineer, use engineered features, which I could talk about that a bit later. Okay, so you had the RGB examples you've seen. So that's 3 features, right? Different color. Now there are 7 features. So that's the example that you see. And then, in fact, they tried different features as well. And that's why I think this is a really good beginning. I think, among anything that you could do, k-means is maybe something really easy to try. So some of this unsupervised method is you don't know, you wanna classify data, right? And then maybe you wanna try it as a starting point. And so those are really good chapter to read. Take a look. Okay, so there's a question about how to pick K. Those are really good questions. Yeah, these are really, it's not simple problem, right? And then so you could pick K because, I want to categorize into 4. Why? Oh, because I want to compare against the Zhu and Brodsky's. Okay, that's also good. But then what if data tells something else? Then that's it's missed opportunity, right? So one way to check objectively find K. As I say, everything can learn from data. So selection of K can be done from data. And then one of the most standard way of doing it is called cross-validation. Okay, how it works is that you get backup data, right? And then you basically groups those data to validation to learning set or training set and then validation set. But in a cross-validation, you actually divide this into using M-fold groups. So here I'm showing you an example of 5-fold examples. So you have here sample N, a lot of data, and then this is also subjective, right? You can pick how many fold you can, and then if you have this is also this is a computational concern. Maybe this is something that it's practically guided decision can be useful here. So here the data is divided into 5 folds, right? And then that the randomly assigned, or you could actually use a bit more guided domain knowledge guided way of dividing the data. And then, so here you go, 5-fold. And then what you do is you train k-means clustering rule on this case. In this case, this is the blue part of the data set. And then you set aside one of the M-folds for validation. And then you do second trial. So in 5 times you can do. And then you train the data on a second trial. The blue parts of second of the M-fold data sets. So you basically do it 5 times. Reason why you do this is the decision rule, or this is a classification rules, could be overfit to the specific data, right? So there's no guarantee that the classification rule learned from one set of data set is universal, right? So this is a way to sort of avoid overfit or check the overfit as well. Okay, so if you're doing right, these 5 trials should look consistent. And then, so I guess that's kind of given here. And then, so you do the training with one of the fold, as I said, the data that fall into one of the fold, and then you test it against that one of the fold. And then cross-validation estimation error in that paper that I was discussing is defined as follows. So this is also, you can come up with, okay. So this is a k-means clustering, and then squared Euclidean distance was used as in a basically cost function. So maybe this makes sense to actually define a cross-validation estimation error in the same norm, right? So that is a logic that you can apply. And then so you try out different k, right? And then you basically sum up that, take the mean of M folds, right? So that you don't rely on one sort of validation and then test validation and training kind of case. So you do that. So that's how it's defined. And then, okay. Then, so here it goes. So these authors looked through a lot. Okay, so x-axis is number of k. So they try k equal 2, right? 2 means clustering up to 20, right? And then, so they're doing 10 folds, right? So this is each cross is 10 times basically, so you are doing that cross validation, the computation 10 times, and then you are doing it with all different, case of k. So there are lots of trials. So that's why cross validation is standard method, but it's expensive. It's actually become impractical at some point. You're really doing a lot of like a big data analysis. So, but it's good to know. You should know it as a sort of starting point, and then you could do you could start from you could optimize this. Okay, elbow curve. To say that. So yeah, so where's the elbow? So like you can see that error get smaller and smaller and smaller. And then at some point, increasing class number of groups actually have diminishing return. Or it's actually not diminishing return, but it just doesn't have improvement. So this is a error distance. So it's the difference between these cross-validation errors. You can see somewhere around 7. It looks like yeah, right? So this is also, you can come up with your elbow definition, or you could do a bit more theoretical, way of defining it. But so this is a one way, yeah, to let your data guide you. Okay, good. So so this is cross validation, and then so they picked Keiko 7 out of this cross validation analysis, right? And then it happened to be raw feature they use is 7 as well, but they use hundreds of thousands of data points. So number of replications is hundreds of thousands, right? It's different, right? Do you understand? Yeah. Okay. 7-dimensional data, cluster 7, and then clustered into 7 categories, and then involving a lot of data. Okay, so here you go. So, and that's shown in a density and velocity plane on the left-hand side. So these, so it's basically the clustering rules were learned, and then the original data can be plotted into this, into the original feature space, right? So for example, cluster, I don't know, it's just really bad here. Can you see it? Cluster 3 is slow solar wind, right? And then it's hard to see, but you can see it. I mean, you could actually have access to probably original paper. 42% of the 10 years of ACE data belong to this solar, slow wind, and that's bulk of okay, data goes there. And then cluster 1, 2, 3, 4, and 7. 1, 2, 3, 4. This one, 7. I'm sorry, 7 and 4 are coronal hole wind, right? And that's interesting. And there are 2, but bulk of the coronal hole wind get clustered into cluster 4. And then a small amount, which I cannot see well, you cannot see either there, get mapped to different cluster, right? So that's interesting, right? Like I find it interesting, data telling us, whoa, yeah. And then, so then you could see interstream solar wind, cluster 2, and then cluster 6 here. And then you could see that cluster 2 is a comparison to cluster 6. It's the density is touch low, or this one is touch lower, I guess, and touch higher. So you could see that, interstream solar wind, one is low density and high density, and I could see how that look in a magnetic field strength, and then plasma temperature, and then you can learn. This is you learn from data, right? So it's not different. It's different from predefined, domain knowledge-based categorization. Data is naturally grouped like this, and then interesting cluster 1 and 5. It's they don't know. Okay, so machine learning, still you have to figure out how to interpret the results. So that's why I think you have advantage. I don't know, maybe you have comp sci background, but you understand physics. You spend really good time of your summer here learning about this. It's good. You really need domain understanding. You have to know what's behind the scene of machine learning techniques, right? Then you are ready to discover what data is telling us, right? Anyhow, interpretability of the machine learning, the results is a big topic, right? Okay, so that's that. And then, oh, thank you, Nick. So this is a you could actually see it in the book that the space without machine learning textbook, and that's a really good chapter or for clustering. And that's what I wanted to pay attention to is that number you cannot see here. Like this number. So this is how much percentage of entire ACE data get mapped to different cluster. What I found it fascinating is that number 5 and then number 1 and then number 5. There are really small amount of data get mapped to those clusters, which you cannot see. But it's still clearly defined, right? They have done tons of tests to get this result. So it is like, whoa, what is this? And then sort of, I don't know, maybe they know by now, but it's maybe 7 years ago. So I just find it extremely curious, right? What is it, right? You might be the one to find out. Okay, good. So, okay, so that's K-means clustering application story. And that's, yeah, hopefully that sets you onto actually doing things with data. I heard that you have lab, right? You have exercise this afternoon, right? You're gonna crunch numbers this afternoon. Okay, he's smiling. Okay, good. Go. Okay, principal component analysis. Okay, so you got a really good foundation now. So you wanna find principal component analysis is yet another really go-to tools, unsupervised methods. You wanna explore low-dimensional space that data can get mapped to, but explain that the variability in the data in the most effective way. And as I say, PCA or the kinds of sort of projection, finding that data projection access that can be actually really good features, could be used in conjunction with k-means. Well, could be fed into neural network, all kinds of things, support vector machines. So it's not like you do PCA and then you don't do anything else. You do PCA, you could do k-means combined. You do PCA, you do neural network, da 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 da. And then you all of a sudden, like once you get comfortable, you're gonna kind of combine, several or at least a couple methods. So basically, don't give up. If you download the data, you install the Python toolkit. Okay, I'm gonna discover. If it doesn't tell you if data doesn't tell you the story, don't give up. Maybe you're gonna feature engineers. Huh? Okay. It's a fun. Okay, so here you go. So you've seen it, and I want you to play. Hello, could you play GIF? So it's a nothing really fun, Okay, so there's like 100 data points, and then the search for principal components. Of course, like that you just have to do SVD, right? You got the data, you do this singular by decomposition. Here you go. But you know that is eigenvalue problems, but also this is a constrained optimization problem. So basically you know you are searching all kinds of possibilities and then finding out the direction coordinate that really maximize the variance of projected data, right? So I just wanted to remind you. And there are different ways to get principal components if you actually go back. So I tell you one of the story from my graduate student time. Actually, I spent my graduate student time here at NCAR. I got the fellowship from NCAR, and then I was given a bag of data from my research advisor here, and I tell you the story. And then, like, you know, principal components or standard way of getting a principal component didn't work. And so I'm going to tell you a bit. So if you understand the fundamentals and then you stumble over the barriers, then you actually can tweak it, right? So anyhow, so the story that I'm going to add later. Okay, principal component in practice is eigenvalue problems. So you want to find projections that's denoted here as U that maximize variance of the data. If you have D-dimensional features, you should be able to find D projection, the principal components. It doesn't mean that the information get mapped to equal, well, actually, you don't probably need that many projections to describe, you know, 90% or whatever the percentage of variance that contained in original data, but in essence, you can get that well in practice. Okay, so that's what you're doing, and then there is eigenvalue problems, and then you can implement like that. And then you don't need to do nowadays, you just call PCA function. You magically get it, but I highly recommend that you actually open the hood, right? And then and because later I'm going to show from yet another paper, solar wind classification paper, that I'm going to show you projected data. So original data get projected to the principal component you find, right? And there's also, even if you know that's not the end game, you might want to do that here using principal component. I'm really like so here you go. So this is my another story, my friend. I'm not really good cook actually. Well, the reason why is because I'm Japanese. I want to follow the recipes, right? And then I forget to taste. So like, well, I don't think about tasting and then modifying the recipes. So to me, like checking all the things, making a plot in data science is like that, checking the taste, right? Okay, you got the book, you got the software, you got the, good professors gave you a code. Yeah, just make sure you check it, right? And that's goes a long way. So it's one way to check it is just make sure that projected data makes sense. Your PCA is PCA doing what it's supposed to do, right? Okay, anyhow, so this is how to do it. Okay, so the there are lots of, PCA, principal component is a very powerful tool, but it's linear projection method. Sometimes it doesn't do the work, doesn't result in intended results or what you want. Okay, so but then if you, let's say, if the data get mapped to our higher dimensional so-called feature space, data can be linearly separated and then can find the principal components, let's say, easily. And that is the idea of kernel PCA. And then, so it uses something called, so this is some picture that sort of you get that idea. And then, so use so-called kernel trick. But then, so here you go. So the problem fundamentally, kernel PCA solving is exactly the same as PCA. It's just that kernel PCA find the projections that maximize the variance of map data. You want to map the data to higher dimensional feature space. And then here, that mapping is denoted here by phi. And then how are you going to find phi, right? That's like yeah, if you know it, we don't need to sweat. But yeah, it's not, but this is a really impractical, and then maybe it's a very challenging problem to find a phi. Yeah? Okay, so then what you do is you're gonna use something called kernel trick. So you don't look for actual phi, you sort of bypass it. And so this is a common trick that you could see in the machine learning techniques. And then support vector machine use that. And then also other you could see other methods that kernel tricks is used. So maybe you can apply kernel trick to different new method that maybe not used. What you look for is inner product, right? So this is phi transpose phi. Here's the inner product. Could you see it? Are you okay with the vector calculus? Okay, so you look for inner product, and then you could actually, when you see it, you could actually apply kernel tricks. So what you do is that use projection rule, here denoted by, so we don't know phi, but you don't need to know, but then you actually hypothetically think that you can do this projection. And then you define some so-called kernel matrix, gram matrix. And then I'm skipping over a bunch of stuff, and that's where to look for the more basic, basic descriptions. It's in all the textbook that the one I found it useful is Christopher Bishop's textbook. And then so basically, so you could see that this problem, the kernel PCA problem, then get mapped to translated into this problem, kernel PCA. And then like the only thing you have to see at this kind of quick description is that phi is gone. So you don't need to actually go look for phi. What you have to come up with kernel. The choice of kernel is a sort of decision that just like you have some of the decision you have to make. So you try and error. So this circumvents explicitly mapping data into feature space. Well, then you could actually do this nonlinear principal component analysis. Okay, so I'm just park that idea because I'm gonna show you the example that George Myers, very nice work that recently published in Frontiers. That I heard that this is also given as a good paper to read, right? George Myers. Anyhow. No. Okay. Yes. Yes. No. Yes. No. I liked it. Okay, I'm not solar physicist. Well, I'm more kind of studying things closer to the Earth. I found it really very illustrative. So another recommendation. Okay, so but anyhow, you're gonna see some plots results from that paper. So instead, I think it's 7 raw features they use from ACE data. Again, 14 years of ACE data, right? And then they use 15 different raw features, right? And then so what they did is just quick forward. They are so one of, there are many lessons learned in this. So again, they try to learn classification rules from data. And then, so rather than doing k-means clustering, for example, the Meissner's work, that, original data set, and then the one that you have seen, in my talk is that they apply k-means to basically raw features. So what they're saying is that you got to do a bit more, or you can layer in different machine learning techniques. And then like, for example, KPCA, and then there's other thing they tried. So feature engineering before clustering, make k-means shine. Okay, okay, and then also they tried their so Gaussian mixture or Bayesian Gaussian mixtures. It's a bit relaxed version of what relaxed or the estimation techniques. It's a bit different. They're using MCMC to find a posterior, but it's also clustering that just like you run a Gaussian mixture method. So they also did that Gaussian mixture clustering, and then so this is the other previous paper that they, and then but then they basically showing you could do a bit more. You get more, you learn more by doing more here in the machine learning, right? That's a lesson. And, okay, good. So here you go. So so this is a data projected onto principal components. So there are 15 row features. So you can find up to 15 principal components, right? And then, but then it's not showing everything, which this is not research done by me. So like, so this I'm showing the things shown in a paper. So it's so there's, let's take this one. So you got the original data, but you can project, right? Because you learn. So this is PCA coordinate, principal component 1, principal component 8, right? And then so you can map all the data, right? To this particular joint space. And then this underneath this contour is you get like tons of data, right? You get projected. And then you can actually connect those data points. And then so those are contour plots underneath, right? So those are projected data, projected original data into the principal component space. And then you could do it all, different combinations because you got up to 15 space to explore, but it's rotated. And then so what it's done here is that, of course, again, interpretability of machine learning result is difficult. You want to verify against domain knowledge-based categorization results. So this is a Zhu and Brodsky's result, 4 categories. So you can see this color is 4 different categories, basically predefined categories. Does that make sense? So like so all the data get projected underneath this line contours. Red part is this is a SH. This is the first solar wind of coronal hole origin. Again, kind of like a clustered or kind of showing up at this area, right? And this joint space. And then let's look at the transient solar wind type, TR here, right? Like it's occupying a different space, different area, right? So this is a cool result. And then you could actually see it, right? Now you know this is a good, well, this sets you up for k-means clustering, so KPC, so PCA, and then you could do nonlinear version of it, right? And then so principal component found by kernel PCA, you just briefly learned, and then you do the same thing. So you could see that all the data get projected, original data used for learning get projected onto this space, and then you could map to the 4 SolarWind predefined categories defined by Zhu and Brodsky, right? Both seems like working well. Well, there's difference. Okay, so let's see. So then once so the workflow is that you do dimensional reduction or feature engineering here, and then you're gonna get another tool, k-means, and then Gaussian mixture model, and then do the clustering, right? So and then so k equal 5 it didn't say that how they found the five. Okay, but it's a so color is randomly assigned to the different categories, right? And I could see that so this is a k-means results on top. The bottom is Gaussian mixture or Bayesian version of it bottom, and then feature is found by PCA and KPCA. And then I could see that just from here that I think clustering, I think a Bayesian version is doing maybe, separating a bit better in a PCA space. But, KPCA, it seems like both equally, well, maybe not, like maybe better here, you know. So this basically it's eyeballing, but you could actually test it with again, you set aside a bit of data for validation, you train, right, with training data sets, and then you can actually test it and then could quantitatively define. And then this paper doesn't stop there, and then they even go on autoencoder and a more latest method to categorize solar wind. And then I think it's really promising areas. Well, as much as I can, somebody could chime in, but I think it's still, it's not like a one method wins, but I think in combination of feature engineerings and then some of those more latest classification methods, I think we can probably learn a lot more, and then of course include domain knowledge. So we can comb through tons of data and then do more science. Okay, so I think this is a application examples of k-means and PCA, KPC, and then Gaussian mixture model. Because I was asked to talk about. So this is the only instruction I was given. And that's okay. So I think I delivered that, hopefully. So this is SolarWind. And then I want to tell you a bit about my story, well, my research. And then, so this is a sort of, yeah, so you see my paper, 2002, ancient. There's no Python toolkit. But still, there are tons of data was given. So I showed up. I as a graduate student, showed up at the NCAR. And then my advisor, research advisor, Arthur Richmond here, he retired by now, or he retired already, was very much into DE2 NASA mission data, loaded with really good plasma instruments. Really, still, I think it's one of really good clean data. So he gave me a bag of data. Okay, and I didn't know any of the thing I'm talking about. So, and then there are no tools. Okay, and then so I was supposed to do. Okay, I was supposed to learn. Principal components from this data set, in situ data, sparse, right? And then I wanted, we are interested in modeling spatial temporal variability or convection patterns, so use the plasma drift data from about 600 passes, right? And then luckily covers all local time, so you're seeing that one polar pass. Okay, so I half year or so, it's so funny. Like it's really good. Like it's really interesting, right? Like even though you are not making any progress, so it's sometimes really interesting happen. And then if you're in that spot in a graduate or postdoc stage, don't worry, just keep going. So I was doing that. I had no idea how to model, how to learn principal components with this crazy sparse data, right? So I was on this ASP, Advanced Study Program Fellowship. That was a very nice thing that I got. Okay, very fortunate. right? I was here, and I'm gonna do something. And so yeah, Richmond said, "Oh, why don't you go to AGU? You're doing something." But but then you write the abstract to AGU without having a concrete result. That's what we all do, right? It's okay. You're gonna get it. Okay, I'm gonna go first AGU, and then didn't get anything. So I was standing in a poster, and I was like really like lots of plots, lots of signal processing, basically all the tools, try to model covariance from this, and I couldn't get anything. But it's Richmond said, I don't want to go. No, you have to go. So I went, and then in a poster session, I really want to hide and standing, and then try to be small so that people don't realize. And then this advanced study program, ASP director. So there's a like summer school director, right? Fund your research. He found me. He found in the poster session, and I was like, no, he's not gonna come to me. And he found me. And then he looked at my poster, and then he looked at me in my eyes. He nodded. Okay. Like this. I got you. Okay. Then I was introduced to this third author, Doug Nitschker. He was also a scientist, and he was a trained statistician. So I was sent to Doug to talk about data. So that was around the time that, I don't know, before or after that summer school. So data science started calling me. But anyhow, so that's that. So don't worry. If you feel you're stuck, maybe you're just at that, day before cusp of, breakthrough. Don't worry. Just keep looking at the data. Okay, so so now coming back to what I'm supposed to talk. So let's see. So plasma. We wanted to model plasma drift, and then let's model plasma drift. Those are the data as a special temporal random fields, right? Stochastic processes, and then let's expand that on model that using Kaplan-Meier basis, which is basically principal components. Okay, so this is a straight out from definition, right? So let's say, oops, I don't know, I went too fast. So let's say X random process at the space and time can, it can be expanded onto principal components as this by Kaplan-Meier theorem, right? And then if phi is again functions of covariance of process X, and then alpha is time, in this case that things changes with time, and then also random process, and that's that variance is eigenvalues, right? So you just kind of flip the problem, right? And then as I said, so I didn't know this. I was stuck earlier getting a D2 data, and then really try to get the sample covariance that I could magically do singular value decomposition or eigenvalue problem. I couldn't because data is so sparse, and that's often the data we deal with in space physics are sparse, right? We don't have satellites all over the place in the domain that we're studying. So these are the things that if you scratch a bit surface, then you have a path to move forward with precious data, but it's difficult data. Then data reveal the secret, right? Okay, so here you go. So as I said, that this learning principal components and then eigenvalues directly from that kind of sparse data was not feasible. So rather than that, we could actually one of the things I had to do is, okay, first of all, formulate a problem like Kaplan-Meier expansion problem. I just want to model process as random field model. And then think about it. And I still want to get that phi and then again values alpha. And then but then, okay, so dimension of the problem is too high. So you can this is something you could always do. You could actually introduce predefined, again, also normal basis in this case. So that, in this case, I happen to use Becker harmonics functions, and then project that, or describe this, assume that this principal components are described in terms of Becker harmonics. So you get that, this middle equations. So dimension, well, degree of freedom got smaller. And then now the problem is that finding alpha that changes with time. And then that only, what I need to do is with this actually correspond to the eigenvalues of the covariance. That's the constraint, well, the sort of, direction. And then the beta is, in this case, spherical harmonic coefficients, right? So you basically, just like I wouldn't call this kernel trick, but for me, that was a trick that time, like translate the problem that is actually solvable. And then now the problem of finding alpha, beta from data is, it's something called backfitting in statistics, but it's implemented as a nonlinear sequential regression. So it's iterative algorithm. So it's a bit, heuristic. Well, it's not like it might get stuck in a local minimum type of thing, but it's still did that work. And then so this is done, and it's a bit more than that, but it's somehow find a way to solve it. And then so this is what you can get from that kind of sparse data set. So this is the principal components. So now, this is so usually PCA is done in this images, and then, now you saw earlier solar wind application. So like a feature space RGB, for example, 3, right? Solar wind data feature space was 7 or 15, right? Now, so the feature space here is the points on a space. Well, I translated that as, well, interpreted that as a spatial problem, right? So, okay. So you could, that's also a decision when you construct that machine learning problem. So here's the principal components that were learned from the 3-year or year and a half of D2 data, and then came out that way. And then, so it's an interesting thing is that, okay, so you can see the mean, and then EOF, we empirical orthogonal function, that's another name for the principal component, PC1, PC2, PC3. And then, so earlier you saw that now this was solved in a very different way than eigenvalue problems, right? Like, or singular value decomposition problem. So I have alpha, time-dependent coefficients that changes with time. So I have time series associated with each PC. So I could do the amplitude, time-dependent amplitude of PC1, right? I have a year and a half worth of time series, and I could get the IMF solar wind magnetic field data. So I have I could do the correlation analysis. When PC1 goes up, then BY was in this case going down, right? So there's anti-correlation. It's not, like this is not spectacularly high correlation, but then if you know the high latitude electrode, the convection, it really, because of the reconnection point changes, this convection pattern rotate with respect to local time. So that's the mode that be picked up as PC1. So again, what I gained by doing this extra work or hard work is the interpretability of the data. Yeah? Well, I could do things like that. So that's a nice thing that I learned from going through a bit embarrassing experience, but I gained something. Anyhow, so PC 2 that is time-dependent coefficients is correlated with BZ. So this makes sense. Two-cell convection patterns, right? Strengthening or weakening. So you could you could see that two-cell convection patterns getting stronger and weaker, and as related to BZ. That makes sense, right? So it's a well, right? And then variance, let's go. It goes down as expected. Okay, so that's one example. And then, so this is another example. And so this is applied to super-down plasma drift data. And then you see, but it's this was done by a postdoc here at the NCAR. I worked with her. And then, so you get that. And then you see that for 6 EOF, and then also the same approach, you could actually do the correlation with, in this case, like an AE, right, or an electrojet, and then could see that, like, gain interpretability of principal component. And then since this is a bit, it's not like a heuristic approach, it goes up and down, I think we could have reordered this variance, well, EOF numbering. So that's another example. Okay, so, and then, so here you go. So this is what my graduate student, current graduate student is doing as I speak here. So he got couple years of iridium next magnetometer data, and then gone through the same exercise, and then, okay, he wanted, so Nick Bartel wanted to understand, using iridium magnetometer data, how field line current variability are different north and south. And then in the past, the north-south symmetry was not clearly separated from seasonal effect. So he gone through tons of data and then did the principal component analysis. Then, so here is local summer map, PC 1, 2, 3, 4, right? And then this is a north, and then this is a southern hemisphere. And this is local winter, PC 1 to 4. And then, like, look, it's strikingly looking similar. North-south symmetry, if you actually compare summer to summer, the PC, in terms of PC, is looking really similar. And that's this is a way, it's just a way to look at that, study the asymmetry of field and current patterns. We still have to submit this paper, but so I think it's interesting. And then, so that's just the pattern that you're looking at. Okay, so then there's a sort of related method. It's called canonical correlation analysis. So this is a great unsupervised method. If you have two groups, two data sets, still unsupervised, you don't have level data. So now we have data from Northern Hemisphere, data from Southern Hemisphere, unlabeled. I want to know that if they're similar or dissimilar. So if you have problem like that, CCA is great. And then again, fast forward, you can implement CCA as generalized eigenvalue decomposition problem. So you form sample covariance, and then another sample covariance, and then you can plug that in if you can get that sample covariance. And that's not what Nick ended up doing, because, well, Iridium is pretty good data sets, but it's still incomplete. We treat it as an incomplete data set. So this is a CCA transfer projection. So this is, you looking at local summer, right? So the field and currents have lots of activities on day side. And then, so that was a principal components show that. And then you can remap it into CCA. And then, so basically reorganize into independent mode that increases, or the projection that maximize the correlation, north-south. So like, this is just a way to look at it. So principal component, north-south correlation, those EOF maps correlation is not particularly ordered by principal components. But if you reorganize in terms of CCA, right? So that's sort of, yeah, you could do things like that. Okay, so that's one example. Okay, so the other thing you could do, well, this is another of my example. Again, space mission data is sparse. And then we wanted to, in this case, well, sparsely sampled. So this is the application of PCA, the version that I shared that works in a sparse data application case. So this is the application to atmospheric mass density. So again, my data, bag of data is CHAMP data, 9 years of CHAMP data. And I wanted to, again, characterize spatial temporal variability of atmospheric mass density because I wanted to get objective. That is, I wanted to learn, well, many of us want to learn what drives mass density variability. And then we wanted to learn not from model, from data alone, right? So this is the objective. And then so you could see that one, this is how mean density look like at the 400 kilometer in the thermosphere. And then you can see this black circles, dots, those are the sampling points. Oh, it's tough. It's sparsely sample. We got the so limited data sets. And then we wanted to, because thermosphere is strongly driven by the sun, and have really strong solar local time variability or diurnal changes. So it makes sense to analyze in this coordinate system, right? So that's that. And then fast forward, crank up those numbers and then code it, going through those learning. And then this is what I got. So you've seen a mean. So EOF1 patterns, PC1 look like this. 1, 2, 3, 4. And if you remember how mean look like, it's basically the leading mode of atmospheric mass density variability is basically sort of modulation of mean patterns. And that is sort of like reinforcing what we already know. It's mass density is driven. Atmospheric mass density at the 400 kilometer is strongly driven by solar EUV. And then in fact, you could confirm that with sort of correlation analysis against F10. Amplitude of PC1 I have, right? And I could do correlation analysis against F10.7. And I'm like, whoa, this is like a really strong correlation. So somebody was asking elbow curve, right? So in this case, it's a really typical case that not typical, but it's a really successful decomposition or mapping. So then a lot of variability is projected to first few principal components. So steep, right? So okay, here he goes, if you actually, do principal component analysis of white noise, what you're gonna get? Well, basically no information in the data set. Then how does spectrum would look like? Yes, flat, right? So that's so that's tough luck. Okay, so here you go. So this is a really, rich in signal, rich in the patterns case. Okay, and then again, so I told you that I have principal component time dependent amplitude, and I could really see what's going on, and so I could see that semi-annual variation, and then also depending on the solar cycle, 2001 is higher, or 2009 is solar minimum this time. That cycle. So it's you could see that amplitude is higher when solar activity is high, right? It goes down. So this color indicate the amplitudes of your PC1 for different years, right? This makes sense. And then have, especially at the high solar activity, you could see this very distinct semi-annual variation. And then you could, so this guides you how to study mass density variability. And then this EOF, two principal components to have interesting annual variation. This is a seasonal mode. And then also So this is the principal component one, amplitude. You could do periodogram analysis using wavelet, for example. So you could see that it's interesting 9-day oscillation popped up. So this was due to recurrent geomagnetic activity due to co-rotating high-speed stream that existed this time. Wow. Yeah, you can learn a lot by, right? Like doing, analyzing data in this way. Okay. So, so that's a example that I think I have. This is all I have. Okay. So I talked about application of unsupervised machine learning techniques to some of the data that you may see in this field, right? And so you learn the unsupervised machine learning techniques, really handy methods to manage large volume data sets by dimensionality reduction, right? And then extract characteristic patterns and trends from data, right? Yeah. And then also identify the way that data are naturally grouped together. Those are clustering. And important thing, don't forget that you're doing this to gain scientific insights. Okay. So are you ready for your data-driven heliophysics science discovery? And then we are counting on you, right? You are entering into field at this amazing time. Yeah. So good luck. Thank you very much.
So regarding the kernel trick, I was just wondering that you mentioned that the projection of the points are not orthogonal anymore. So does it mean that one is trying to move the problem into different space where it becomes orthogonal? And if so, how this space is chosen?
So again, space, you mean projections are also learned. I mean, I try to understand your question. So projections are learned also from data, right? And then so it's a, I mean, it's the only thing is projections are not obvious, let's say, in the original space. And then you assume that you kind of get, maybe this may not be the true, right? Always, am I understanding? You have to stop me because I didn't really fully understand your questions, but it's you just in this case in an application sort of side of how to find out is that okay? It doesn't work.
Maybe if you can I can just refer to that figure that you were showing that in some spaces you can just draw a straight line, but in some spaces you need to draw a curve.
Right. So yeah, okay. So yeah, curve. Okay. So yeah. So this is a Christopher Bishop's text spec. So this is a original space. So we don't know that this green line, right? But it's a but then we want to learn this green line that is basically orientation of this projection. Wow. And then this is not learnable in the original space. But if you map to the phi1, phi2, is that you map this original coordinate system, data lives in the original coordinate system to feature space. And then this cartoon is not like there's one that's actually, I think it really helpful is it's 2D to 2D, right? Looks like. So like let's say that imagine that you have third dimension in the original data space. And then you look like this, if you map to 2D, data live like this. But then in a third dimension, the data that let's say, like around here, like projected the higher in a z coordinate, x3 coordinate. Does that make sense? So like imagine that if you project this data to higher dimension, which is, let's say 3D, that these data are like become linearly separable in this case, for example.
Okay, yeah, just to summarize, I think the idea is to be able to find coefficients for phi which are unknown to define this new space.
Makes p
Phi, the phi. This phi.
yeah, well, we defining phi is difficult, and then we already given up. Well, at least in the practice, we don't. It's hard to find this projection. So in practice, but then yeah, I'll try. Thank you for your question. Yeah.
I had a question. So is there a standard practice for when you're doing k-means, which 2D dimension you end up plotting whenever you publish? Because we're trying to do a similar project where we're doing a k-means and we want to be able to plot. And I was wondering, is there like something you can look for? I mean, visually, I'm guessing you just look through the images and you figure out where there's the most like visual spread in 2 dimensions, even though it's multi-dimension. Is there a standard for picking that you look at, or is it just look through the data?
Thinking for your own paper, so you could actually show the joint space. Is that what you're asking? Like one, like you could stack it up, like you could show, let's say D1, D2, and then second one, D1 to D1, 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 D2, the kind of thing, and you could show the projection in a different joint space. Am I answering
Yes.
like? But then you have 100 dimensions, and then
Yeah.
you run out of paper.
Yeah. So I guess it's normal practice just to try to visualize some of it, choose what looks the most appealing, or maybe show some number of things.
So I think, yeah, I mean, I think figures in your paper, like, machine learning analysis, you wanna present in your paper, and then like I always come back what I want to learn from data, what is the point, what is the discovery. So if you are sending this to like a JGL type of thing, then you should showcase that, right? Like you don't need to probably show everything, because right. So that's maybe you could choose which dimension that you want to project to. Is that what you was asking? So
You're
yeah,
saying
yeah,
like
that's right. Like
cater the features you highlight towards, I guess, the audience, or I guess the purpose of the paper scientifically.
yeah, audience or point of your paper, what sort of accentuate, highlight what you have learned. I mean, if this is a really science that you're getting out, if you want to showcase, hey, I apply really fancy method that no one did, then I will highlight that. Like, okay, this worked, right? So but depending on what you want to show, but it is true. It is true that you cannot show everything.
Okay,
Yeah.
thank you.
Mm.
Just wondering about the clustering of the data.
Clustering data.
Yeah, the data clustering. So you showed an example, solar wind.
Mm.
We did the clusters over 10 years, right?
10 years worth of data
Yes.
fed into.
So my question is, what's the physical insights you gain from, for example, saying, oh, this cluster have the same density, right? But this is over 10 years. Like, okay, at certain time, these densities were produced
So
different physics, right? Different physical conditions.
yeah. So yes, you learn the clustering rules from 10 years worth of data, the general rules, but then you can project the data that sampled solar min, solar max, right, into those categories, right? And then you could see the time series, for example. So you could see that cluster 1 actually pops up a lot in solar min. And then cluster 7 pops up a lot more in, the time that we know that, CME is. Well, those are the things that you could use to interpret the results as well. So it's not like you get that, you have it's actually in a paper. I think it's the Ameyer's paper, I think, had the time series example. Active time, and then quiet period, and then the clustering rules learned from 14 years of data get mapped to the original data, and it can show as a, you can see that time series, and then see that how like one type of category of solar wind more frequently occurs in a particular time. But it's best that you look at that paper.
Okay.
But I'm not sure. Like, yeah. So those are the thing that you could if you don't want to use 14 years of data, maybe you want to just use a solar max period or declining phase or something. That is also another way to learn from data, right? You might learn different category, and then you could see the cluster similarities. For example, there's no one way to do it, but you need a sufficient amount of data for your results to be, maybe, valid or, universally applicable. Because if you train the model on a smaller samples, that like basically you're just learning about that data set, right? So you wanna learn, in this case, clustering rules, and then you wanna apply to different time, ultimately, right? I guess you're hungry, right? Like, okay.
No question, right?
Just one question.
Okay. So
You're between everybody else and lunch.
I'll be around, so I can stick around and have lunch with you guys, and then. But please do.
okay, just let me know if my understanding is correct. So since PCA uses linear mathematics, so linear algebra, so when we have a problem which is not linear, so we transform it into a space where we can separate the data into a linear separable space, right?
Mm.
And so when you do the kernel trick, we have to choose the kernel, right?
Yes.
So how do you choose the kernel?
Yes. It's a very tricky problem. And then I think what I do is try out different kernels, and then you could actually optimize as a sort of a parameter. You could try different kernels, and then it's like a choosing K for K-means. It's an open question.
Okay.
It's not easy. It's not easy. So like each time you go to a bit more advanced methods, there's a price to pay. So the choice of kernel is, I would think, price to pay. And then sometimes you get lucky, and then you have to try a lot
Okay.
sometime. Okay.